Alright, last two questions for me for this year. Woohoo! Question 10, this is the truss bridge shown in figure 4. It rests on these 2 points here. There's a truck in the middle, which identifies the beams that are compression or tension. The easiest way to do this is just to have in your notes somewhere that this is compression, 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 that's in tension, 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 tension. And the ones that follow that rule are beam EF is in compression, so this one, and beam FG is in tension, this one and this one, and beam EFH is in compression, this one and this one, so the answer must be B. Let me do question 11, I'll come back to doing the explanation for why that's the case if you want to stick around. I'll just do question 11 first. Alright, there is an arch shape. As soon as you read arch, you say compression. And there are steel cables. Cables can only ever really be in tension. Right, that answers the question before I've even read it. Which of the following correctly identifies the components which are in tension and compression? Alright, cables, you can't have cables in compression, they'll just fold over. So either this or this. And arch is always strong because they're always in compression, here or here. So we've got answer B. Right, let's just go back up if you want to see the explanation for why these beams are the way they are. Okay, so let me do the external forces on the bridge and then the actual forces within the bridge to hold it together. So there's a downwards force here of gravity from the truck and from the centre of gravity of the bridge. So we're coming from there, and there's obviously, to counteract that, from the ground there's an upwards force here and an upwards force here. Alright, in blue, I'm going to do the forces that the bridge does. Now, what we do is we look at each point. It's not sexy enough blue for me, I need. No. There we go. Look at each point and make forces equal to 0. Right, so let's look at this point here to start with. Obviously, if there's a downwards force, there needs to be some upwards forces. So from here, there's got to be an upwards force and an upwards force to cancel out with that downwards one. Within the beam itself, within each beam, the other end is equal and opposite. Okay, so that's going to be there, and that's going to be there. Then you've got to say, well, is that tension or compression? Anything where there's a beam and there's the forces going inwards, they're pulling inwards because they are tension, like a rope. Pulling inwards, that's what a rope does best, it pulls things. If you have a beam and the forces are pushing outwards, you have something under compression. So all of a sudden we've got this one here in tension and this one here in tension. Alright, that makes sense. Good stuff. Let's have a look at this point here. Now we don't want the beam falling over. We don't want it pulled down. So there needs to be some pushing up to cancel out with that downwards arrow. So at that point there needs to be a force pushing up. So that means at that point there, the opposite, there's going to be a force pushing down. So if we're pushing outwards, they're in compression, which is what we've got there. Cool. Now let's look at this beam across here. We've got one going, let's just draw those arrows, one arrow here and one arrow here. If you add those arrows together, you get an arrow going that way. We need to cancel that out, so we need an arrow going the other way here. So there's an arrow going there and the opposite going there. So when they're pushing outwards, that's in compression as well, which is what I got. I can do the same working for this side as for this side because it's symmetrical. So that must be under compression as well. Good. And then we've got these last two here. Alright, so if we look at this one here, we've got a downwards force, we've got an upwards force, which means overall we've got, these are these two forces here at this point, we've got a force that way. So we need a force the other way, so at that point we need a force there, which means it's the opposite goes here. When they're pulling in, they're in tension, which is what I got, and it's going to be equal and opposite here. Pulling in, tension. So that's how I ended up getting for this structure all the compressions and the tensions. If they give the same structure and you've already got this in your book, then you know how to do it. You can just copy the right compression tensions in there. If not, that is the method that you go through to find out. You look at each point and you make the forces 0. The first thing I did was the easy forces that I knew. There was a normal force upwards from these guys to hold the bridge in place, and there was the weight force downwards from them. And then I started from there.